Okay, so I want to finish off the first bonus video with a hand wavy argument, because I don't want to go into the detailed maths about the higher order and lower order possible solutions that we could have depending on how we're fixing the beam either side. So at the moment we've assumed that we've got a hinge where this is allowed to move up into the first. If I compare it to my sine wave, we assume that it's going to follow profile like that. This is one point, this is another point. I reflect my two hinge points like that. Compare that with the cos of the same frequency, so we're doing pi in terms of frequency. Cos looks like this, and so we can see that that doesn't fit. So the sine works, so therefore I'm going to choose that as a good fit. Now let's consider the case where we're going to fix this side of the beam into the wall, so we're going to embed it, so in effect that we're expecting the gradient to be fairly flat. So I'm going to have a flat gradient like that, but the force that I'm applying is allowed to kind of deflect off this jack here. So although we've got a force being applied in this direction, still we're going to let this move up or down. So we could have a solution possibly where we've got the hinge there, and it will look something like that. So what possible solution could we have there? Well, if we compared that to the sine, where we would want a gradient to happen here, and I will make this my length. Okay, so here we could see that we could get something like that, so it would fit into a sine wave nicely, where we would set the length to be pi over 2. Right, so what other possibilities do we have? And again, if we looked at the cos, well, the problem with that is that we're pushing down and we've got a flat tangent here, so it doesn't match up this, so that doesn't work and that doesn't work. Next one I could consider would be that I don't allow this thing to shift. Okay, so I'm going to now push this down. I'll have it pinned, and I will kind of let there be a slight a slight sort of line up here like this, and so that will look something like go up, go down, and then we'd have to sort of like try and get this to be as flat as possible. So the best kind of fit that I could get, and to be fair, it doesn't quite work, does it? But the best kind of fit I could get would be something along the lines that we've done this much of the sine. So it doesn't quite fit. We've slightly displaced it, so this doesn't fit with this, but it's a pretty good match for in terms of a shape. So that would be 3 over 2 pi. Looking at our cos, well, we've gone for a frequency like that. So this one here, you can see the gradient is not going to match up with this gradient at all, which needs to be as flat as possible. We've got a very flat gradient there, so we don't want that on the left, so that doesn't work at all. So let's finally consider trying to fix both ends so that we're going to push them together. Imagine they're in some sort of cup or something like that, and push them together. What's going to happen this time? So it's going to go up, and then I suppose it would go down, and then it'd try and go in like that. So it would be doing something along some sort of double wiggle here. So the sine is not a good solution, because we're now trying to make this flat. We're trying to make this flat. We've ended up back to the beginning, but here we're going off at an angle, here we're going off an angle, so that doesn't work. This time the cos is actually a pretty good match. Okay, so this time we could use a cos as a solution, and we would set that to be the length such that we got 2 pi. So the various cases that you've got is you've got something which looks roughly like beam fixed. You're applying a weight there, and you're going to have your length is going to work out to be, well, let's write out my solution. You're going to have your root P EIL equals half pi. So you can see with this, if we bring the L down over to the right hand side for now, just leave this PEI over there, you've got 2L here, and this is often called the effective length. So the effective length is a 2L case. Next case is where you've got two kind of hinges being pushed in, and it just kind of buckles like this. And so we've seen the solution for that. That's PEIL equals pi. And so that's going to therefore give me that the effective E is L. And what about the next case, which was where I've kind of fixed the bottom, and I've now applying this thing here, and we're going to imagine that we get some kind of half buckle, and then it goes as flat as possible. And that one, that's a bit more approximate. We've got L equals 3/2 pi. So therefore you've got your L is 2/3, your effective L is 2/3 whoops, 2/3 L. In actual fact, the correct answer is 0.699 L, often taken to be 0.7 L. You can see 2/3 not far off from 0.6999. So that was a pretty good model without doing any complicated maths. And then the final one is where you kind of squash in here, and I'm imagining getting something like this. So a good model for this would be now to use cos. So we'll switch to the cos, and we would have to use 2 pi's worth of cos. So this would then be that we would have pi. Let's write it so that we've got it in the same form, and that gives us then half L. So our effective length there becomes half L. Okay, so you can see how you kind of get the different end conditions. You're just going to look them up on a chart on Arnold's formula sheet, but that's a hand wavy and reasonably nice way to sort of explain where those various effective lengths come from without going into many complicated maths.